Zhao is a colleague of yours?
Oh, yes, yeah. Celebrating the first anniversary of our journal, Sustainability and Circularity Now, or SC Now as it's affectionately known by us. My name is Dr. Charlotte Marshall, and I am the senior publisher for the journal, and I'm delighted to be here to be moderating and hosting this very special session today. You're very lucky in that we have an excellent lineup of speakers for you, including the editor-in-chief of the journal, Professor Chris Slutveg, who will be helping to chair today's session and helping moderate the question and answer sessions after each of the presentations. We also have talks from a selection of our fantastic associate editors and authors of the journal, who will be showcasing their work and involvement with the journal throughout their presentations. I can't move on. Let me try, click over here. Lovely. Okay. So before we formally begin with today's special seminar, let me provide just a very brief overview of some of the key points to help facilitate today's session. So you may already be aware that the seminar is being recorded, and that's so that others who haven't been able to make the live recording are able to watch the session afterwards. To avoid any interruptions within the presentations themselves, we have put the audience on mute, and that will continue to be the case throughout the webinar today. However, we do very much encourage the asking of questions, and so we would like you to use the question and answer window within the Zoom functionality, and we will try and ask as many questions as we possibly can at the end of each presentation. So please feel free to add your questions as and when you would like. We would love to hear what your thoughts are on the webinar, and you can do that by sharing your thoughts on our various social media channels by tagging us in, either using the journal links or the Team of Chemistry ones, which appear on the screen right now. We have LinkedIn, Blue Sky, and X accounts that you can contact us on. And if you're interested in hearing more about our Cheminar series or subscribing to our Team of Chemistry newsletter, the links are there for you on the website there. Okay, just talk a little bit more about the Team of Chemistry portfolio itself, just for a couple of minutes before I formally hand over to my chair, Chris. So for those who aren't aware, TEMA is a German company with an international presence of over 130 years of experience in publishing science and medical information. And Team of Chemistry is a branch within the TEMA group, and we have traditionally specialized in organic synthesis, so helping chemists acquire knowledge about organic chemistry, as well as helping devise efficient synthetic strategies. So you may well be familiar with our products such as Science of Synthesis, which is our full text resource for methods in synthetic organic chemistry, pharmaceutical substances, which is our online knowledge base for API synthesis, patents and applications. But we also have a range of journals such as Synthesis, Synlet, Synform and Synfax, and organic materials. Sustainability and Circularity Now is pushing the boundaries of terms of the areas that Team of Chemistry specialise in to broaden our scope to involve areas such as sustainability and green chemistry. So it deviates from that traditional organic synthesis and broaden and expands those horizons. And in that vein, we also have a suite of biomedical journals that aren't shown on the slide, which include drug research, Planta Medica, and psychiatry as well. But talking more about our main journal today, which is why we're all here, Sustainability and Circularity Now. It's our newest journal within the Team of Chemistry portfolio, and it's open access. It is focused on the most serious challenges pertaining to sustainability and circularity, helping to shape the ambitious and interdisciplinary nature that we would like to resolve the global crises that we face. And the idea is really to unite and facilitate scholarly, public and policy conversation across the globe to help solve these crises. So as you can imagine, with that kind of title and that kind of aim, we have a very broad scope for the journal. And you can find out more about that scope at the link that is provided on the slide, or also using the QR code there as well. There are many reasons to publish with us, but some of the real key factors are our aim to contribute towards UN SDGs. Our journal actually goes a step further and puts the Sustainable Development Goal logos on the papers themselves, the relevant ones which the author chooses. We have the approval from the UN to do this. So this really helps our authors to easily demonstrate to their funders and to their communities how their work fits in with these UN SDGs. We also have a unique reviewing option available called Select Crowd Review, which is Team's answer to scientific publishing through this fast, interactive and modern approach. Conceived by Nobel laureate Benjamin List in 2016. The process aims to enhance the peer review through crowd-based evaluation. There is more information available about this on the TEMA websites provided, and we'd be happy to discuss this with anybody. If you would be interested in becoming one of our Select Crowd reviewers as well, please just get in touch. Okay, so I think we're ready to go, Chris. So let me just introduce you for a few minutes. So Chris received his undergraduate education from VU Amsterdam in 2001, with research stays at the University of Amsterdam and the University of Sussex. After earning his PhD in 2005, he pursued postdoctoral studies at ETH Zurich with Peter Chen. He started his independent scientific career in 2006 at VU Amsterdam, and he was promoted to associate professor in 2014 and moved to the University of Amsterdam in 2016. The mission of his laboratory is to educate students at the intersection of fundamental physical organic chemistry, main group chemistry, and circular chemistry. Chris is the co-founder and scientific advisor of SUSFOS BV, a pioneering company focused on upcycling phosphate-rich waste streams to generate high-quality alternatives to replace current fossil-sourced products. I'm delighted to say he begins 2025 as a full professor of circular chemistry at the University of Amsterdam. Many congratulations again, Chris, on that. And as I mentioned before, he is our fantastic editor-in-chief for our journal. So I'm delighted to hand the floor over to him. Thanks, Chris.
Thanks a lot, Charlie, for this wonderful introduction, but also for, I'm delighted to work together on this new journal that we're now celebrating its first anniversary. I'll highlight why I think sustainability and circularity now is in particular important with sharing a few pictures. So let me share my slides. So it was August 1, so the 1st of August, when I was preparing for a lecture to give at a scientific conference, the Gordon Research Conference on Green Chemistry, actually. And just about I was about to present my slides, I spotted this picture because it was published on August 1. And it highlights Earth Overshoot Day, highlighting that in August, we already used up all our natural resources, meaning that September, October, November, December were depleting our resources. And for me, this is the most important argument to focus on circularity and to focus on circularity now, because clearly the way we started developing our society since the Industrial Revolution was good, but now clearly signs of needed improvements are highlighted in various aspects. And so this picture is something that I think with the mission of the journal, we really like to contribute to sustain. So what type of topics are in need of more sustainable advances? And Charlie highlighted this already. And for me, the foundation of the planetary boundaries really sums up the key domains that we need to sustain our research and the use of products in society. I mean, climate change, obviously, it's basically the redox chemistry of carbon, greenhouse gases spoiling the environment, but now also nutrients, excess nutrients are ending up in the environment, causing undesired effects, which also need major attention. Not to mention the impact of all of these planetary boundaries on the biodiversity. But maybe first and foremost, man-made chemicals that enter the environment unintentionally, sometimes intentionally. So these new design chemicals, think of PFAS, think of plastics, think of herbicides, all very useful chemicals for their function. But if they also enter the environment, it means they need a serious redesign, serious attention from everyone across the globe. So that's why sustainability and circularity is so important, in particular to do it now, because we still have major topics to tackle. And as the mission of the journal is highlighted here, Sustainability and Circularity Now aims to tackle the various serious sustainability issues. Of some I've just highlighted, and shape an ambitious and generally interdisciplinary agenda to resolve the global crises that we face. So it's focused on chemistry, but not only chemistry, from molecular design, material design to the engineering of that, including environmental scientists, because only together, we can tackle these global challenges. Not just research, but also the impact on companies for scale up and having societal impacts next to scientific impacts, and the policies that are urgently needed also to be able to impact new technologies in society. What I also like, and Charlie mentioned that, is our profile in social media, in particular, just recently also on Blue Sky. So Sustainability and Circularity Now really triggers Blue Sky research, but also it really focuses on an open environment where we can openly discuss all the important aspects of today. Now, one aspect that Benjamin List for SynLab developed, and that we're also using, is the select grad review. And so traditionally, if you submit a paper, it is sent to 1, 2, 3, 4 reviewers that are selected by the editor. But SC Now also offers the opportunity to be part of the crowd, to be part of a community, and really as a community to review a scientific paper and give the authors some feedback. So we really would encourage, if you would like to be part of this community, to apply to become part of the select grad review, simply by sharing your CV and application letter with us. The email is indicated, the email address is indicated on the slides, but you can also send it directly to me, for example. As long as you want to be part of the crowd, just give us a a shout out, and we'll take up this challenge together. Next to working with the team, I'm also very grateful to work together with our associate editors. I mean, they're all listed on the slide over here. Julia, Anand will be speaking today. Sylvia will also speaking. Georgie, Regin will also speak today. Peter, Vanya, Masaharu, and Jesus. And it's really wonderful to work together with such a broad community of editors and together shape the focus of sustainability and circularity now, and offer basically a wide portfolio of scientific articles that will help the community and society progressing in terms of our sustainability challenges. Just to give you an idea, I mean, many topics are of course suited for the journal, but we also have special issues to give you some guidelines, what topics are also of interest. Biomass conversion, CO2 utilization is one of our special issues. The second is on solvents. Solvents are key for making molecules and materials, but they also can be sustained to quite a certain extent. So this is also a dedicated topic that we focus on, and the design of molecules and materials, in particular the safe and sustainable design is a special focus topic where of all these three currently they're of course open for submissions. But just to give you a brief idea what papers have been published already in our inaugural volume. I mean, I won't highlight all of them because also the speakers of today will highlight their contributions, and there are many more. But just to name a few, the focus on circular chemistry is really important, and that was highlighted also again in the journal as a focus on sustaining chemistry, sustaining chemical technologies. And if you think of Earth Overshoot Day, we have to close the loop. And so this is an urgent message to integrate in our thinking. And the second, just as a specific example for making molecules, you want to do that with as low impact as possible on the environment, on the economics, and so on and so forth. So can you mix ingredients and make the desired molecule safely, but also, for example, is the most sustainable solvent, just use no solvent at all, but still being able to perform the chemistry, of course. The other is something I quite like, because maybe not only because it comes from my group, but this is actually directly targeting, can we more sustainably use nutrients for food production, and at the end of the line, can we actually recover those nutrients from waste stream, for example, from human urine. So this was quite a fun project to actually showcase the potential of being able to reuse urine as a fertilizer, because all the nutrients are still in there. But of course, after cleaning it up, basically removing some of the possible contaminants. And this is just simply focusing on the fertilizer itself. But then, of course, another paper really dives deep into the application of fertilizers using field experiments and also calculations. And so this really shows the broad focus of the journal, from production to use to implementation and to recycling. Another which I quite like is from Frank Curtin. It's really about the use of biomass, for example, to make composites, to be able to use them in drug delivery systems. So we focus on materials, molecules, sustainability challenges at large. So quite a variety of topics to educate researchers, policymakers, and students. I think all of these topics are really crucial. So to me, if you think of sustainability, and you think of the way we've developed science and chemistry in particular, we really need to focus on it quite differently, is my opinion. And circularity was mentioned. It's in the title, but if you think of sustainability and circularity, to me, this is really the three pillars that we need to advance. Is sort of focus on production of anything we need, because it has properties, it has a certain function that is desirable. Think of medicines, think of materials in general, and the production has to be done as efficiently as possible, of course. But second, and this needs to be included in the design and execution and use, is that the products need to be used circular. So we cannot waste resources. We should not waste resources, because remember, we need to secure them and use them again simply for sustainability purposes. And this is the most important one, to be able to use resources more efficient. So this can differ per product. If the product should be designed to be durable, or to be reusable, or for example, that's a closed loop system where it's recovery and recycling, for example, like for nutrients, needs to be implemented. Depends on the products, but at all times, it's an ideal circular system has to be designed. And then, of course, whenever we do any regrettable substitutions are not nice. So we need always to include safety for humans, animals, and in general for the environment. So to do this together, it makes a challenge a multidisciplinary one, and a really exciting one that we need to propel with the focus of particularly. So with that, I would once again invite you, if you're not already in the crowd, to be part of the community. We really much invite you to share your contributions with us. And I would like to already thank our speakers for their contributions, and much looking forward to this webinar. So I'll stop sharing, and then I will start introducing our first speaker. And just before I do that, I would like to highlight that if you have any questions, just post them in the chat during the talk, because I will select the questions at the end during the Q&A. So if you already have them, just put them in the chat, and then I will do my best in pushing out questions that will be discussed with the author of the talk. All right, so then we'll go to Anand. So Professor Anand Kapi from the Institute of Chemical Technology, Mumbai, India. He's our first speaker of this exciting webinar. He started his scientific journey at the University of Mumbai, but then went to York for his PhD, worked as an Alexander von Humboldt Fellow in Göttingen, and then returned to India. His research focused on catalysis as an enabling technology to make molecules and materials, investigates mechanisms, but also develops fluorescent bioprobes for metal and protein sensing. So he has really a broad interest in sustainability, and he also uses quite innovative techniques for that, like flow chemistry, which is already indicated in the slides. Anand and Mori, more than happy to work together as editors for this journal. I very much look forward to the talk, which is going to be the slide highlights, focus on making nucleosides and also commercially relevant compounds using flow chemistry. So Anand, with that, the floor is yours.
Thank you, Chris. Thank you, first of all, for creating the platform perfectly for green chemistry and sustainable chemistry. The slides, what you have highlighted, I think makes my life easy as well. I'll be discussing with you some of the recent work that we have been doing in the area of nucleoside modification, but we have, rather than doing the general catalysis, we also thought that we could try to apply expedited methods such as flow chemistry, which is now more relevant in the current era, given the fact that there have been various issues which have been related to batch processes, especially with respect to the hazards related to batch process, as well as formation of byproducts and various other problems. So my second slide rather gives a clear overview of what issues batch process have been having. I think this shows that these are not small disasters. Some of them have been massive disasters all over the world. And the reason being the pressures which are developing in batch processes cannot be easily handled. Sometimes they lead to major disasters because it's like a runaway process. In that regards, in the last decade or so or more, flow chemistry has been introduced effectively around the world, while like Europe and America has already been using quite efficiently flow chemistry, but it's slowly coming into India and various other countries as well, where batch processes, the problems associated with batch processes have been slowly been taken over by the introduction of flow-based technologies. Idea is very simple, that rather than having big space which is required for batch, you can probably reduce that space into something which is very effective, very efficient, and you can still scale up to the level as what you expect from an industrial scale process. And this has been effectively shown by companies such as BASF and various other companies on a very large scale as well. And you can see a small representation of a flow reactor, where you have these microchannels which are available and through which various reactants can come together, react very rapidly. The interactions between the molecules can be enhanced to a much larger level. The rate of reactions can be enhanced very rapidly as compared to batch. There have been examples of how difficult batch reactions for lithiation, nitrations, fluorinations have been taking place, with a lot of hazards which have been there with respect to high temperature or very low temperature reactions, as well as the reactivity of some of the reagents. But the flow reactor, now this is one example which has been given, that you don't need a lot of space. It's a very restricted space, and still you can get large quantities of product formation. Plus the fact that you can work with very ambient temperature conditions, which is not possible for like a batch reactor. So lithiation can still be carried out at room temperature as well, which is previously not possible. And nitrations can also be carried out at very low temperatures, minimizing the risk of problems associated with batch reactors. How we got into this was, we have been working extensively in the nucleoside modification area. The idea was to develop these fluorescent probes. Various anti-HSV as well as anti-cancer agents have been known, and we have developed a lot of catalytic reactions which can access these type of molecules very effectively. One of the problems associated with Suzuki, the coupling chemistry or the type of modifications that we do is certain byproducts which are forming, which I'm going to discuss about. We have been able to develop one of the ligand system in our group itself, which has been very effective in coupling reactions, for specifically the nucleosides, nucleotides, as well as Heck reactions, Suzuki coupling, and a variety of reactions in water itself at very low temperatures. The only problem was, whenever you're carrying out this reaction in case of, let's say, batch reactor or something which is like a flask reaction, which are the general conditions which we do in the lab, you would always get some byproducts, and the isolation of these reactions, the product isolation would always take place using column chromatography. Now, column is not desirable on industrial scale or large scale processes. How to avoid column or all the other problems associated with column, how to avoid even formation of byproduct, is something which is of interest, not just for academia, but even from the industrial point of view. So we tried to first analyze a general batch reaction, which could be carried out in a normal flask. And what you see is a reaction which is carried out with a catalyst like palladium, nickel, always requires temperatures which are 60 to 80 degrees, timelines which are around 10 to 12 hours, and you have to maintain the conditions which are anhydrous, plus the fact that you have to use nitrogen or argon as a gas for keeping the conditions effective. The main reason is a palladium can also get oxidized over a period of time, and then you get very poor reactivities. So in order to have a catalytic system which effectively works under the condition is not always easy. Plus the fact that you will always add some kind of byproduct. Now this is like a hydrodehalogenation reaction, while byproduct formation from the homocoupling of boronic acid is also well known. This complicates the overall isolation procedures which are there for the formation of the product. And that's why column chromatography is the most commonly used technique for separation of these byproducts from the products. Now, what are the parameters which we need to keep in mind if we want to then take it up into the flow? Is first of all, the time requirements. For a batch reactor, it's several hours. 12 hours is a very long period. That means even it could be called as an energy-intensive process in terms of the timelines. A requirement of an inert atmosphere, definitely, because over a period of time, any oxygen or any kind of moisture coming in can always kill the catalyst. So having nitrogen purging and argon purging for such a long period is not beneficial, or it's not very useful. It also escalates the cost on a larger scale. Hydrodehalogenation, as what I've shown already, and the homocoupling reagents, it is a big problem, and it is promoted under the oxidation conditions. So if you have moisture or oxygen, this will always promote the formation of more of byproduct. Solvent is a big problem, because not just a reaction solvent, but at the same time, the purification using column chromatography would be, in a small scale process, it could be some liters, but in large scale, it could go into much more amount of wastage of, excess use of solvents. We have been collaborating with Stephen Hilton from UCL, University College London, and he has been able to develop this ICA flow, which is a kind of an easy plug and play type of flow reactor, much easier for chemists to also understand how to use flow. And we have been fortunate that ICA was able to provide this equipment to us as a demo unit. And two of our students, one of our collaborative students from Rambabu Dandela group, as well as my student Santosh, has been working extensively on this area. The idea was whether we can convert this batch reactor process into a more of a flow and try to reduce the timelines, as well as work on certain conditions, what I've already discussed about. And what we were able to achieve was, first of all, reaction conditions can be developed in such a way that you can avoid the use of excessive solvents, you can avoid the use of column chromatography, and the conditions can be suited in such a way that you can do the reaction without nitrogen or argon purging at lower temperatures and with very small timelines. Now, it is important to understand that solubility of the reactions or the reactants in the solution is very important, because anywhere you have possibility of precipitation of the product, it can probably clog those microchannels, what we had seen in the previous case. So we have to use the choice of the solvent very, very carefully. In our case, we had used ethanol, which solubilizes not just the product, not just the base and other reactants, but also all the other material, which generally would be, it might be a possibility that the catalyst might also, it can come out of the solution and it might clog. So we had to take care of all these things. We had to do a lot of optimization. And finally, we were able to come out with a condition where ethanol water system works the best. The reaction, if carried out in batch reactor system, what we saw was it still takes around 3 hours. And the reaction gives you 84% product, but you get 10 to 15% of the byproduct. While in case of flow, reaction rate, if you keep the flow rate, and this is a setup which has been shown, this is where the flask, which is there, ethanol and water. This is where the injectors are there. You can inject your starting materials with the catalyst, and on the other side, you can inject your base and other things. And then it goes into a loop reactor here. It gets injected, but everything is pressurized using normal air. So air pressure is used rather than nitrogen or argon, which means the reaction should proceed only under normal air. The reason being, palladium or nickel or any other catalyst, oxidation is a slow process, so it takes longer period. So if you leave it for a longer period, for 3-4 hours, definitely it will, it will degrade or it will deactivate. But in a shorter period of time, which is maybe few minutes, it should not be a problem. And that's what we are able to achieve. That this reaction proceeds up to 95 to 97% product formation without any byproduct formation. Residence time overall in the loop reactor is around 8 minutes 45 seconds. And the total amount of solvent required, which is methanol and water, is only 15 ml. At the end of the reaction, whatever you have isolated as a product, it is pure product, single spot, and you can simply evaporate to get pure, product as such without any further purification by column chromatography. Now, this is very effective and this is very useful. You might have to do some amount of solvent, you want to use some amount of solvent just to remove the inorganics, and small amount of organic solvent to remove any other previous starting material or anything which is remaining. But overall, it's very quantitative amount of yield which you get, and you are not seeing any kind of byproduct formation. This has been then applied to a variety of substrates. So we got very good yields of most of the substrates, especially for uridine. And then we are also able to take that for cytidine, works very well. Now, the question was, in case of cytidine, we were seeing slightly more longer reaction times for batch reactors, which is around 24 hours. But in case of flow, we could simply do the reaction within 29 minutes, nothing more than that, which means that you can almost complete 10 or 12 substrates in the whole day, while otherwise it would have taken 10 to 15 days. The reason being, 1 day is a reaction and then at least 1 day for purification of your products. Sorry. Now, in this case, we are able to also think about scaling up. And scaling up is very important to demonstrate that if flow reactor can be used once, twice, or can you do it in batches, in several loops as such. So we were able to continuously do a reaction for 18 injections with 8 minutes, 45 seconds as a residence time, overall 3 hours, and you can get almost gram scale, 1.67 grams of the product can be obtained very effectively. And the overall solvent which you are using is water methanol, 180 ml. And at the end of the reaction, what you are getting is almost pure product. So what we did for Suzuki coupling, we also wanted to do it for Heck reaction. And there was a very important reason for that, because there are various drug molecules which also can be synthesized using Heck reaction. So the simple Heck reaction with flow reactor works very well. All the conditions can be developed very well. 29 minutes is the timeline, and 80 degrees is the temperature, and the reaction proceeds very effectively to give the coupled product. But idea was something to prepare as a drug molecule, and this is the drug molecule which is BBDU. This is anti-HSV agent. The general procedure takes around 3 steps. The reactions are generally 8 to 10 hours, in some cases 3 hours. But overall, almost like a whole day or 2 days, which will be taken for purification of all these various steps to give you the final product, just pyridine. So we were able to get all these, and what we saw is the overall yield was not very effective. It's around 40–50% overall yield that you would get. So in order to improve this, when we tried to go for a full-fledged flow reactor system, what we were able to observe was you can do 2 reactions effectively in flow continuously. You don't have to isolate the product. So you can get into the formation of the Heck product, then you can hydrolyze it using sodium hydroxide very effectively to form CVU, which is a carboxylic acid. But then the next step, which is the formation of the BBDU, which is a bromination step, what we saw was, in general cases, some amount of product would fall out of the solution at the end of the reaction. And that's why we decided not to go for flow reaction as the final step. But even after doing that, as a normal batch reactor, the overall yields jumped up to around 86% as an analytically pure BBDU at the end of the 3 steps. Overall timelines have been reduced much more drastically as compared to what we had seen previously. And that's why you can see that there is a lot of benefit of flow reaction, which can be applied to this type of very important commercially useful molecules as well. We also switched to a collaboration with DRILS. DRILS is Dr. Reddy's Institute of Life Sciences. They work extensively with flow reactions. Dr. Srinivas Oragunti, who is also one of the part of the paper, is also the main author of the paper. We decided to work on a commercially relevant molecule, and the important molecule which we decided was CPC. So this is a cetyl pyridinium chloride, very important structural feature, and has shown a lot of applicability in industry. What we decided was, rather than having a batch reactor, we have comparisons of batch reactor, but then converting into flow and try to reduce the timelines from something like 48 hours to only 30 minutes to give you very high yields of the product. If you look at the importance of cetyl pyridinium or any kind of tetra-ammonium substrates, they have been used. There is a lot of biological relevance with respect to acetylcholine chloride, but at the same time, a lot of importance of these tetra-ammonium substrates in industry, especially CPC. It has been used in mouthwashes, toothpaste, throat and nasal sprays, Very important because it's a powerful antiseptic as well as antibacterial properties. And you also have surfactant properties, which is generally expected because you have a longer alkyl chain, and then you have a quaternary ammonium species which is present. The general idea was when we have carried out the batch reaction at 110 to 130 degrees, overall timelines are around 48 hours. And what you are seeing is you get in some cases very good yields, but you are using excess of pyridine up to 4 equivalents. The overall timelines are not useful or feasible when it comes to scaling up, although commercially it's still happening that way. What we thought was if this could be then converted into flow reaction conditions, we should be able to work on these timelines very effectively, and we might be able to also come up with a better condition for the amount of pyridine which has been utilized. And we were able to successfully do that. This is kind of the setup what we had in drills. So you can have a flow reactor. This is the loop reactor which was present. And then the timelines can be reduced only to 30 minutes. So we have worked with this 200 degrees, 100 degrees, 160 degrees, which I'm going to present. But what we saw is at 200 degrees temperature, is slightly higher temperature, but the reaction goes very cleanly into the formation of CPC with very high yields, and the timelines are only 30 minutes. So one thing which is that the volume of solvent what we are using overall in the previous cases have reduced drastically, and the final product is almost quantitative. So which means that you can use it without less amount of purification. You don't need much purification as what we have done with respect to batch reactor. So these are some of the results which are there. In most cases, you see the reactions almost quantitative. Timelines are very competitive, 30 minutes, 15 minutes that you can work with. 200 degrees is slightly higher temperature, but it's like offset. So either you can go for lower temperature, but then the reactivity can be compromised. But then if you are going for very high reaction rates with respect to the molecular interaction, what you have in flow reactions, you can get quantitative yields of the product without much of a problem. If you then compare from batch to flow of the space-time yield, that means the amount of space which batch reactor requires and the yields which output which is being shown in literature, batch fails miserably. It's around 8, while flow is very high with respect to 1050. Now that gives you a very good comparison that if you want to scale it up, let's say into metric ton scale, batch processes might take a lot of time, almost 24 hours conversion rates, higher temperatures, and overall 3 batch cycles to get into the metric ton. Well, there is a possibility if you compare with respect to flow, you might get away with this with a smaller space of the reactor which is required, and you can still get up to 3.5 metric ton per week. That's something which is a proposition, and we are looking at possibly commercializing this process as well with some company. Finally, I would like to thank the group, definitely Rambabu as a collaborator in the first paper, Srinivas who was a collaborator in the second paper, my students, and the amount of funding which various companies and all the organizations have given. I would like to thank Circ Now for giving this opportunity. I'm really happy as an associate editor. We had a lot of discussions. Chris, is great to have you as an editor-in-chief, and really looking forward to a great year again for Circ Now this year. Thank you.
Thanks so much, Anand, for this wonderful overview and also your dedication to the journal. I really like that you showcase the use of flow chemistry to sustain chemistry, chemical production. And the lecture is now open for discussion. So I see there are already a few questions in the chat. Please add your questions to the list, and then I will highlight them in our discussion with Anand. So just to start, Julian also highlighted batch chemistry or batch processes, which are traditional also in industry, and the advent of using flow chemistry. So what are for you the most important advances or advantages of flow chemistry? You named a few, but what are really the deal breakers?
I think if you look at the hazardous reagents which are commonly used, which rather have led to a bigger problem in batch reactors. So for example, when you are looking at high temperature, high pressure processes, working with some hazardous gases, I think carbon monoxide would be one. The amount of the requirement of these reagents in flow reaction can be controlled to the most minimum. While in case of batch, unfortunately, you have to have higher pressures. That means excess of gases, and that leads to the majority of the problems. So working with smaller contents of hazardous chemicals at any point of time, if certain things go wrong, you can isolate that system pretty effectively, which does mean that you can have, you can reduce your impact of, the problems associated to the least. While in case of batches, we have already seen that runaway reactions cannot easily be stopped, especially the radical-based reactions. They just go into a complete explosion. So I think that is a very, very effective way of controlling some of these processes, because the space required and the control what you have on the various reactants is much more effective.
Yeah. Thanks for highlighting that once more, and also to elaborate on that in a bit more detail. So a follow-up of Julian is also, I mean, there are clear advantages, flow versus batch. But how do you see the implementation on the larger scale in industry? Because I can imagine industry, if you have a chemical factory available, which typically costs quite a bit of money, and you have a process running, then the incentive to develop and design an entire new process or plant is maybe not there. But clearly flow chemistry has major advances and can even the production become way more effective and affordable. So do you see any hurdles in implementation, or do you see it already happening on the industrial scale?
I think if I look at it from the developed countries' point of view, and I will bifurcate in that way, that there is a lot of incentives from, let's say from Europe and America point of view, where flow has been implemented on pretty much larger scale. I think what you said is right, that when it comes to space requirement and the existing setup batch, which to be removed and then implemented as flow takes a lot of cost. Flow reactor system also not very cheap as such. So a lot of investment takes place at the start. Actually, it will give a lot of dividends at a later stage. But the reluctance comes from the fact that you will need to invest first. So then it comes to the developing countries where the reluctance will be much higher. However, if what I see is, if there are many companies now which have come forward who are selling, flow reactors all over the world, even India we have, and various other places as well. I think there has to be some dialogue or some way that there has to be like a small demonstration possibility of some of the problems associated with industry, any particular industry or several industries, from that company point of view, to make them realize what's the real potential and how long it can go. I think then the realization will be higher, and most probably then the switch can take place to a much larger extent.
Yeah, I fully agree. And also, if you think of adopting new models, new systems, new processes, it also depends on us at large. If we're eager to take up the new challenge, and so then it basically boils down to education. And so and then I'm speaking of University of Amsterdam, our education at bachelor master traditionally was focused on batch processes.
Yes.
But we realized if there are new technologies and ideally you want to implement them at large, we also need people who recognize this opportunity and know how to work with that. So is this also what you're implementing in education yourself, for example, just to showcase you know, a continuing broad audience, that this has much merit.
Absolutely, absolutely. I think in India, one person, and maybe he is there in the audience, Professor Anil Kumar from IIT Bombay. I think he has been doing a lot of lectures and a lot of implementation in the academia as well. Personally, I have what is called as developments in organic synthesis, and this is exactly what we have been discussing. This is part of that course as well, where not just flow, but you know, ultrasound, microwave, all these technologies are introduced to the master students so that they see the relevance of these technologies in day-to-day life in the current scenario, and what would be even the future of technological advances which are taking place. Yes.
Yeah, that's exciting. And so a very specific question from Professor Depp that I will read out is connecting to your message. It basically flow chemistry can ease up product purification for product separation, but in one or maybe more examples, you also showed that there is a side product in low amounts, like 10% of the iodo case, where you want the iodo product, but there is a little side product. Could you specify how you were able to separate the side product?
Oh, maybe I should be very, you know, what I was trying to suggest was this was a batch reaction which was done. In case of flow, we are not seeing any of these products. So this first reaction, if you see, this is a batch reaction model which we have created. So model flask reaction. This is where we see always some amount of, let's say, deiodinated product. But when we go to flow, we don't see any of these deiodinated as well as the possible homocoupling of the boronic acid. I think the simple reason is these are all time-based reactions. Over a period of time, moisture or anything which comes into the reaction, already water is there. So your palladium probably then interacts with water, and then you get this hydrodehalogenation reaction as a side product formation. But flow doesn't have that possibility because your timelines are so short, and your compounds, you know, reactants are reacting at a much rapid rate. So we are not seeing anything, and that's why if you see the almost it's a quantitative conversion to 95 plus product formation. So that's where we don't need to have then column chromatography as such for any kind of separation. It's almost like a single spot formation all the time.
Yeah, that's cool. In the chat, Tony also highlights that Monash Masters of Green Chemistry also advocates flow chemistry and use it as part of their curriculum, which is really exciting to hear. Just another topic that I would like to hear your opinion and views, because a colleague of mine here at the university, Timothy Noel, he also advocates flow chemistry. And he also likes to integrate it with robotic platforms. And at first, this sounded to me, I mean, maybe in some aspects traditional, but anyway, it sounded to me as quite an adventure. But his thoughts were, you know, the data that is currently in the chemical literature may have some deviations from the true conversion yield, let's say. Because it requires workup. If you spill a bit, it doesn't matter. But then you get different numbers out. In particular, if you would like to use machine learning and AI to predict and optimize the ideal reaction conditions. So for that, he uses flow chemistry with an inline NMR, where without any human interference, you get spot on data that indicates what is under these reaction conditions the conversion, and then the machine learning takes over in predicting the better conditions, let's say. And I thought it was pretty exciting application of flow chemistry. But is this something that you recognize, and also do you see other modern technologies and opportunities for sustaining chemistry?
I think so. I think inline technologies are definitely being used. Even previously, they have been used for characterization and so on. But this does make sense because, as what you suggested is right, you need to have a very clear-cut idea because we are predicting that the reactions proceed very effectively, and you might not get any other byproduct or anything. It's a very clean reaction. But quantitatively, unless until you isolate and then analyze, that takes longer period. And maybe during that time, especially in catalysis, you might always have the reaction continuing. So if you have an inline process, especially what has been now done, that if you have NMR which has been directly attached, I think it makes life very easier. It's the same thing with respect to online GCs, that if it's a gaseous reaction and you directly get it injected into the online GCs, you get a real-time understanding of what's the process and how much conversion is happening. So I think this kind of is the future. This probably will give us more handle, over how such technologies, which are disruptive technologies, they are very important technologies, how they can be enhanced further to make it more effective, much more efficient. And I think that will make people realize as well what would be the larger use of these technologies, really.
Yeah. Thanks for sharing your thoughts, and Anand, thanks a lot for your contribution and the discussion. I really enjoyed it.
Thank you. I'll just stop sharing.
Yeah. Thanks again.
Thank you.
Let's continue with our second speaker. That is Professor Hujian Liu. And she's from the Institute of Chemistry, the Chinese Academy of Science in China, of course. So I would like to ask to share your slides already, and then I will continue the introduction. Her research really specializes in the conversion of renewable carbon resources, like biomass. Think of CO2 into valuable products. Really to focus on renewability at the front end and making compounds we always need. She has received notable awards such as the IUPAC Third World Green Chemistry Awards, as well as the China Catalysis Rising Star Award, and she contributed to numerous high-impact publications, but she also holds 4 national patents, which I thought was really nice to mention. Really grateful to work together as you're another associate editor of SE Now, and I'm more than happy to offer you the stage online to showcase your work on the efficient transformation of biomass to valuable compounds. So the floor is yours.
Sorry, maybe. Okay.
No, don't worry.
I will start my presentation. The title of my presentation is about efficient transformation of biomass to valuable compounds. And
if you like, you can also put your video on. It's up to you. But yeah, please continue.
Sorry, maybe I cannot. Okay, now it's okay.
Yeah, no, please continue. Yeah, thanks.
Okay. My presentation consists of 4 sections, and the first one is the research background. And this is a carbon cycle diagram. Biomass is considered an important renewable carbon resource that can be formed through the photosynthesis, fixing carbon dioxide. It also can be transformed to coal, petroleum, but because this process is very, very slow, so we don't think coal and petroleum is a renewable carbon resources. Currently, the energy and the major chemicals we use primarily come from fossil resources. It is very important to substitute fossil issues by biomass, since the process carbon capture is much slower than carbon emissions, which leads to the carbon dioxide accumulation. So we also think the converting carbon dioxide into important chemicals is a critical area of research. Our research is focused on the transformation of waste biomass. The important principle is do not contend with people for food and do not contend with food for the land. The existence of wasted biomass polluting the environment and nor the utilization of waste biomass is very low. The structure of biomass includes 3 parts for the cellulose, hemicellulose, and lignin. Since the complex of structure of the biomass and the inert chemical bond, it is a great challenge to achieve the efficient transformation of biomass. From this graph, we can see an important characteristic of biomass. It has a high oxygen content. If we want to achieve the transformation of biomass to hydrocarbons completely, deoxygenation is necessary. Of course, due to the high oxygen content in biomass, we can utilize its structure to produce important oxygenated chemicals. The fundamental scientific issue is the activation of carbon-carbon and carbon-oxygen bond. Below, I will introduce several works we have conducted in the transformation of cellulose and hemicellulose derivatives. 5-hydroxymethyl and furfural are an important biomass platform, and they can be obtained from cellulose and hemicellulose. They can be further transformed to valuable compounds. This is the HMF hydrogenalysis reaction path. It is very complex. Although many kinds of compounds from MF are useful, well, it is very difficult to get one compound with high selectivity. We need to think about why is the catalyst selectivity low. The main reason is that the adsorption mode of the reactant molecules on the catalyst surface is not selective. Among these compounds, there is a very special one, 5-MF. Why do I say 5-MF is special? Not only because it is a very useful compound, but more importantly, both kinetically and thermodynamically, it is very difficult to obtain MF through the hydrogenalysis of MF. From kinetically, hydrogenation of carbon-oxygen double bond is easier, and thermodynamically, 5-MF is unstable. Even if we obtain MF, it is easily to further hydrogenated to DMF. In the literature, if they convert to the carbon-oxygen single bond to a carbon chloride or carbon iodide bond first, and then further hydrogenate to obtain MF. We developed 3 types of catalyst to achieve this reaction: single atom catalyst, platinum catalyst, encapsulated PVP or niobium oxide. The selectivity of MF all can be achieved above 90%. The first example is the single atom catalyst. For this type of catalyst, it has the single interface, which leads to the single adsorption mode. An interesting result, we found that different single atom catalyst mental species only affect the activity, while in nanoparticle catalyst, the mental species affected both selectivity and activity. That is because hydrogen activation occurs at mental size, while HMF activation takes place at niobium size, like this. The catalyst has a single interface and lead to the single adsorption mode of the substrate, so we can get very high selectivity of the substrate. The second example is this catalyst, platinum encapsulated with PVP. Due to steric hydrogens, HMF cannot be activated on the platinum surface, but selectively adsorbs on niobium surfaces. As hydrogen molecules are relatively very small, they can still activated on the platinum surface. The activated hydrogen spills over to the niobium surface and reacts with HMF. the selectivity of MF can be reached 92%. The selectivity HMF adsorption on niobium surface determined the selectivity of the reaction. The other useful compound can be obtained by HMF hydrogenalysis is DMF. It has high energy density and high octane rating. It also can be used to synthesize aromatic compounds while DS idle reaction. The current catalytic system needs high reaction temperature with low selectivity. We developed a palladium and copper bimetal catalyst with body-centered cubic structure, achieved selective hydrogenation of HMF to produce DMF at room temperature, and optimal conditions a yield of DMF up to 93.6%. It is interesting that the selectivity of DMF depended strongly on the crystallographic phase of palladium copper nanoparticles in the catalyst. The palladium copper with BCC cradle structure catalyzed the hydrodeoxygenation reaction selectively with 93.6% selectivity of DMF. However, the palladium copper with FCC cradle structure promoted the hydrogenation of the fluorine with only 9% selectivity to DMF under the same reaction conditions. In this picture, we can see that the reaction paths on palladium copper with the BCC cradle structure, the reaction path is very simple, but on the catalyst with the FCC cradle structure, the reaction path is very complex. So we can get very high selectivity on the catalyst with the BCC cradle structure. Except the transformation of hemicellulose and cellulose derivatives, we also do some research in the conversion of lignin. Transforming lignin is a complex and a challenging task due to the involvement of multiple reaction pathways and intricate molecular structures. We need to draw inspiration from the study of model molecules to ultimately achieve the transformation of real lignin. For this compound, it is a model compound of lignin, stand for the lignin structure. We developed a bimetallic catalyst with two types separated active sites. Through synergistic interactions between two distinct active components, efficient activation and conversion of carbon-oxygen bonds have been achieved. From these results, we can see that when the spot was titanium dioxide, the physically mixed platinum and nickel catalyst has the same activity with the integrated palladium nickel catalyst. However, when the spot was niobium oxide, the activity of integrated catalyst was much higher than the physically mixed. It means that the synergistic effects are related to the support's hydrogen spillover ability. We proved that this conclusion using ZAFs combined with ACT-RD and DFT calculations. From XPS, we can see that the WO3 was reduced in the presence of the catalyst with titanium oxide as the support, but it cannot be reduced in the presence of when the support is niobium oxide. Detailed reaction kinetics were studied. It gave us a good chance to determine the active sites for these types of catalysts because they have a separated active sites. There is a obviously induction period for the catalyst. The results show that the quantity of platinum active component affects the length of the induction period, while the quantity of nickel component affects the reaction rate. In this experiment, we can see that in the presence of platinum, the WO3 was reduced since the hydrogen spillover, while in the presence of nickel, WO3 was not reduced. This indicates that platinum active component activates hydrogen in situ nuclear magnetic resonance, and IR characterization indicate that the platinum active sites activate hydrogen, and the nickel active sites activates the hydrogen-oxygen bond. This compound is a monomer of lignin. It has carbon-carbon double bond and a carbon-oxygen double bond. The product alkanes are also kinetically unstable product. We also developed a zinc nitrogen carbon catalyst under the optimized reaction conditions. The yield of product was 75.5%. This reaction involved two steps. The active center for the first step reaction is the acid-base site on the catalyst surface. The active site for the second step reaction is zinc nitrogen active site. Except aromatic structure, there are many methyl in lignin structure. In this work, we propose a strategy for selectively converting lignin methoxy groups to produce pure chemicals. In this reaction, we achieved the transformation of lignin, the methoxy group, to acetic acid, and the other lignin transformed to the lignin with the hydroxy group. Only acetic acid was detected in the liquid product for this reaction. This is the first example for successful high selectivity production of key chemicals from lignin. We summarize the strategy and construct for the transformation of lignin, and we construct a multifaceted synergistic catalytic system to achieve selective cleavage of carbon-carbon and carbon-oxygen bonds in lignin structure, enabling for utilization of all lignin components, achieving the economic economy transformation of lignin. In this review article, we summarize our recent work in biomass transformation, focusing on the transformation of biomass into nitrogen and oxygen continuum, as well as aromatic compounds. And we thank for the funding, the support of the funding, and thanks Professor Bussingham for the support, and thanks for our students and colleagues. Thanks for your attention.
Thanks a lot, Weijin. It's really exciting to see your developments on using renewable resources like cellulose, like hemicellulose, and like lignin for the production of important compounds. The talk is again open for discussion. So again, I would invite you to post your questions in the chat, and then I can address them directly to the speaker. So the first one is from Julian, and he mentions what difference does it make if you convert cellulose from fresh virgin biomass, used biomass, so for example from furniture, or from processed biomass, for example from cardboard. And so could you elaborate on that?
Okay, for the transformation of cellulose and hemicellulose, we just studied the transformation of the HMF and MF, but for the transformation of lignin, we used the native the naturally biomass. We can just convert the lignin and retain the cellulose and the hemicellulose.
Okay, that's exciting. And does it matter which type of biomass you use?
Yeah. Yes, for some reactions, the types of lignin is very important, but for some reactions, it doesn't matter. For example, for the reaction of this one, we just transform the transformation of methyl group in lignin and to produce the acetic acid. For all the lignin, they have the methyl group, so it doesn't matter for this reaction. But if we want to get some aromatic compound, the types of lignin is very important because the structure of lignin is different in different types of lignin. For some lignin, they have a lot of carbon-oxygen bond, but for some lignin, they have a lot of carbon-carbon bond. And for the lignin, they have most chemical compound is carbon-oxygen bond. It is easier than the cleavage of carbon-carbon bond. So the yield of the product is different.
Yeah, exactly. And I mean, it really highlights that your conversion or your reaction conditions using the catalyst is quite robust if it can handle different qualities of lignin, for example. So could you say something about the catalyst development, because that's a crucial part in the research you showcased. Can you, for example, use directly catalysts that are already applied in industry for the conversion of fossil carbon to products, and now the feedstock is entirely different? So does that mean you also need to develop new catalysts? Could you elaborate on that?
Yeah, I think I don't have a catalyst that can be industrial. So I think it is very important to develop the catalyst, a good catalyst, a robust catalyst for the transformation of biomass. But it is also a greater challenge because for the transformation of hemicellulose and cellulose, it is easier. But for the transformation of lignin, the separation is very, very complex. So we have a long. It is very difficult. I think maybe we should try.
Yeah. Thanks for highlighting that, because that also means that the conversion catalytic is important to develop further, which you showcase, but also indeed the separation. So Ham also alludes on that and mentioned that as it includes a series of steps typically in separation of lignin derivatives. Do you have any thoughts how we can make it easier to separate compounds that have, for example, the same polarity?
Yeah, the method we used to separate lignin is very complex, but in the literature maybe they report some methods like using ionic liquid to dissolve the lignin. But it's easier, but we also need to use the amount of solvent is very, very large. Yeah, the step is easier, but we needed to use a lot of solvent to separate the lignin.
Yeah, and I mean, I can guess it would be challenging to use flow chemistry that Anand just highlighted. But in terms of reducing the amount of solvent, flow chemistry could be advantageous. Do you know if flow chemistry is already applied in biomass conversions, or is your group, for example, working on that?
No, I don't think so. I don't know. Maybe we can try. Maybe we can try, but I'm not sure it can work. Maybe we can talk about it's a new method for the transformation of biomass.
Yeah, cool.
Yeah.
And so Zach highlights is the demethylated lignin water soluble?
No, it's insoluble in water, although it has lots of hydroxy group, but for this lignin, the structure is changed. Most carbon oxygen bond changed to carbon bond. So for this lignin, it is not insoluble. It is not soluble in water.
Yeah. Okay. Yeah. Thanks for highlighting that. So during your presentation, I noticed that you use noble metals, platinum group metals as catalysts, which makes, of course, total sense because often these are quite active. But do you see also a shift to the use of more abundant metals for catalytic conversions, in particular using biomass?
Yes, non-noble catalyst is ideal, but sometimes we thought the lifetime of noble catalyst is better than non-noble catalyst. If we want to, we need to think about the lifetime, not the non-noble or noble. If the lifetime of the catalyst for the non-noble catalyst is the same as noble catalyst, we should try the non-noble catalyst. But most of the times, the non-noble metal catalyst, the lifetime is worse than noble catalyst.
Yeah, no, that's a good point. It really matters about the conversion. Can you maybe even recycle the catalyst after, which actually happens for the noble metals, and what's their activity and selectivity, because those are also determining factors in the costs of the entire process, not just the metal itself. Now, good point. If you compare conversion of oil to molecules and now shifting to biomass, do you also observe catalyst poisoning? And so in particular, the starting material contains many functional groups. So is catalyst poisoning also an important aspect to consider and to develop catalysts that are less prone to that?
Yeah. It's a very important issue, and I didn't introduce our work before. We test the poisoning of the catalyst because there are lots of like salt and sulfur in the biomass. They will be poisoning our catalyst, and we also have developed some strategy for avoiding this. Like maybe I can show you the catalyst like this one. We encapsulated the active site with PVP. The lifetime of this catalyst is better. Maybe you know this one, and this one we're using a niobium oxide encapsulated the active site. This catalyst is robust in the presence of salt, soft, the compound points in the catalyst. But for this catalyst, it's robust in the reaction conditions for the biomass.
Yeah. Thanks for highlighting that. So in the chat, just another question popped up. What is actually, in your opinion, the most sustainable way at this moment in time of for converting lignin into valuable products?
Sorry, can you repeat your question?
So for using lignin and converting it into valuable compounds, what is, in your opinion, the best or the most sustainable way of doing that?
Simple way. For the transformation of lignin, we can get phenols and in our lab, but the yield is very low. If we can achieve the all the group in the lignin to the valuable compounds, I think it's very important. We need to think about the atom economic for the transformation of this complex compound.
Yeah, no, exactly. And well, just a short comment that I observed here in the Netherlands, that one of the quite large startups, Avantium, they focus on the synthesis of bioplastics, and they focus on using biomass, also similar to what you highlight, to make furane building blocks. But recently they also started focusing on textiles, because if there is a textile or clothing waste available, which actually there is globally, then that can also be sourced and basically upgraded to similar molecules that can be used in material molecule processing. So do you also see from your viewpoint other sources that in terms of waste sources that are important to consider?
Yeah, I think you mentioned is that the lignin can be used to prepare some new materials. It is a good way, because maybe for this material the types of lignin it doesn't matter for the transformation to material. We just need to care about the properties of the material. Maybe it's better in this way. It's better for the transformation to the compounds.
Yeah, awesome. Thank you so much for your lecture and for your contributions also in the discussion. So then let's go to the third speaker. I really love it that we have such a diverse list of speakers from various backgrounds, also focusing on various important topics to sustain and make the production a little bit more circular, one step at a time. So our next speaker is Julian Louten-Wijs. So Julian, please start sharing your slides, and I'll continue your introduction. Julian is a passionate advocate for the circular economy with a business management background. So another key facet that we focus on in the journal, to basically convert opportunities from lab to market. He's pursuing a PhD focusing on the circular entrepreneurship, while actively contributing to international circular economy standards. So if we create a new system, how to basically monitor that and inventorize it. And so previously also co-founded the sustainability focused startup. So I really like the entrepreneurial focus, Julian. And he will talk, as indicated on the slides, about opportunities, but also challenges of piloting circular business models. So with that, Julian, the floor is yours.
Great. Thank you so much for the introduction, Chris, and the opportunity to present some of my research here that I did together with a range of industry professionals who are more involved in the cases that we're going to be looking at. But I'm happy to get the opportunity to speak about something that's maybe a little bit out of the main topic of this seminar. So I'm excited to take any questions, even if you feel like it's a basic question, because I certainly had a lot of basic questions about the chemistry focused presentations. And so I want to encourage everybody to ask any kind of question at the end. And I hope you can take something away from my presentation here. So I don't think I need to go too deep into why a circular economy is relevant. I think Chris has given a very clear presentation in the beginning of why we need to move towards circularity. But of course, in order to do this, we do need innovative processes, we do need new materials, but we also need new business models to operationalize these innovations and this shift towards circularity and sustainability. But of course, anything new for companies especially always bears risks, and risks always lead to aversion. You don't really want to go into a very risky environment as a business leader. So the question is, how can we actually move past this risk, or why in the first place are circular business models risky? They're not just new and maybe not as well known as linear business models or more traditional business models, but they also have some inherent complexity. So just to give you an illustration of this, I brought you this classification of product service systems, and you can see just in this small example of a type of circular business model, the complexity and also the difference between new and those traditional business models that we're all more used to. So a product service system can be product oriented, which means classic selling of a product, and then you're selling some services. I think everybody is familiar with this, when you maybe have some maintenance services or customer support afterwards. And then there's a use-oriented product service system, which means that the ownership is shifting from the user to the seller, or in this case, the organization, the company that is renting off a product or offering some kind of subscription model. So the user still has the product in their hands, or are driving the rental car, but the product itself is still owned by the company. And then lastly, we have a result-oriented product service system, which just sells the outcome. So you're not even using the product yourself, you're essentially just receiving whatever benefit you want to pay for from the use of this product by somebody else, for example, the company that is producing the product. So you can see that there are some complexities, and of course, if you want to retain ownership of a product, you have to make sure that it gets back to you. So you're talking about things like reverse logistics, which is something that companies a lot of times have not really been dealing with, because they sell products, they go to a user, the customer, and then the customer ultimately has to deal with how to get rid of this product, whether they can recycle it, resell it, or just trash it. So this is just one of the many challenges that come with circular business models. So it's understandable that businesses say, this is difficult for us, and we are trying to understand how we can implement this in an economically feasible way. But of course, we also want to advance this transition. We want to accelerate this transition. We want sustainability and circularity now. I think the journal title is very fitting. But how do we reduce this risk for businesses? And this is kind of what this is about. So we can test those ideas, and there's three categories, if you will, of testing that I think many of you are familiar with. So the first one would be prototyping, which is a very, very simple sketch idea of something that you can share ideas with. You can use it as a tool for communicating. Then there are experiments, which are more in-depth, basically. So I know that experiments, of course, are very common in chemistry, but in a business context, maybe you'll talk about a minimum viable product, MVP, where you have the core functionalities of a product or a service that you're offering to some test customers, and you're getting some initial feedback. So this is great, and it can already reduce uncertainty because you're getting some real data back from the customers, from the market. But it's still a bit basic because, of course, you're only offering a minimum viable version of what you really want to do. And then thirdly, we have pilots, which are more extensive. So essentially, you're offering the full scope of a new business model or a new product service, but you're offering it for a limited amount of time, which reduces the risk, of course, because you can just scrap it after the time period is done, or you can take elements of it. So this is really where you can move from the kind of testing phase to how can we actually make this work? And those pilots, they are usually run over a longer period of time than a prototype or an experiment. So you're looking at usually at least a few months, if not several years, which also makes it more difficult to collect data on pilot projects because it's just a longer process. And in research, of course, those longer term studies are what is really interesting to us, but it's often difficult to get this kind of data. So we have some qualitative data. It is an exploratory study, if you will. So this is case-based. This is not super generalizable, but it gives us some interesting indications of where the circular business model situation is going right now and how organizations are dealing with those complexities and risks. So we looked at several pilot projects that were run between 2019 and 2022. They were publicly funded, so they did not have to pay for all of it themselves. I think that's also why these projects were able to get off the ground at this point. We had 12 projects that we looked at in total, and 5 of them we classified as remanufacturing focused business models. And 7 of them we classified as product service system business models. We had a range of qualitative data that we analyzed. We had some surveys that were done from before and after the pilot projects. We had some descriptions where the project leaders just described their business models. And then ultimately, after we analyzed all this data that was available from those industrial consortia, we talked to a range of circular business model experts to validate and kind of put into context the data and the findings that we generated. So just to give you an idea of where those projects are situated, in case you're not already familiar with the R framework, we put it into a graphic here, a figure. And our focus is on those points here highlighted in red. So anything basically that goes from the use phase to the use phase optimization, if you will. So extension of use is what the focus of those projects is. Remanufacturing and then PSS, product service systems, contain all of these other R's here. So what we're not doing is we're not doing the design phase, the very initial part where you're choosing different materials, for example, and we're also not looking at the end of life phase, so the recycling or energy recovery that goes all the way back to production. So we're kind of here in the middle with those projects. And to give you a more tangible idea of what's behind the results that we're going to be looking at very soon, I wanted to show you 2 exemplary cases, or just introduce them to you briefly. So on the left-hand side, you see a product service system case where it was where a consortium, so this is always industrial producers, manufacturers, or just companies working together with research institutions and other organizations with universities on those projects. So they were all also steered basically from the business, but also from the research side. And on the left-hand side, you have a project that focused on commercial real estate. And when you are renting out a commercial space, then of course a company wants to design it, decorate it, has maybe specific requirements for noise cancellation or something like that. So it's the interior finishing that always has to be redone when a new tenant comes into commercial real estate. And this is what the project is trying to reduce the waste that gets created by always having to redo the entire finishing of a space. And so this is where they're trying to bring back the materials that were used for finishing, where they try to reuse products that were already used in a different way. And so that was what the focus of this one case was. And the other one on the right-hand side is more focused on remanufacturing. So here they had e-bikes that they wanted to remanufacture. And part of the problem here was that the spare parts for these e-bikes were not widely available. And that's why they decided to implement additive manufacturing, so something like 3D printing, to create those spare parts and then be able to remanufacture the products. So just to give you an idea what's behind, because now we're not going to be talking about the detailed processes of the businesses, but more about how their motivations, challenges, and the perceived potential for further development changed over the course of those pilots. So starting with motivation, I think it was quite interesting here to see that before the pilot projects, the general motivation seemed to have been more to increase the sustainability credentials, basically, of the businesses that were involved. So sustainability targets were the main kind of driver initially. But then you can see here by those bar charts that we're showing, and of course we're looking at a very small case number. So this is just a general trend. I wouldn't, say this is like a so-and-so % increase, because we're dealing with small numbers here, just as a disclaimer. But I think it's interesting nonetheless to see that, for example, financial aspects really rose in terms of motivation for circular business models. And I think that goes to show that they started to see some financial potential, but they also see the financial challenges in circular business models, and they see the value of discovering those financial specificities, basically, and understanding better how it can be integrated into their own operations when they implement a circular business model, and so how that can be done in a financially viable way. But then also we see some market pull factors. Here on the left-hand side, you see what's included here. So for example, what the customers want, and also reputation that can be improved through offering circular services and products. So these are some things that we're kind of raising in the awareness and in the motivation. And then you see that also resource availability became more important. So we can infer from that probably the consortia, the companies, realized that through these circular business models, they can also ensure that they have better resource supply. Then next up, we're going to be looking at perceived challenges. So here we decided to create this a little more creative figure, maybe, just to show you more the relative changes, rather than giving you some percentage changes here, again, because of the small number of cases. But I do think it also shows an interesting trend. So before the pilot projects, market-related issues were the biggest ones. They thought this was going to be the biggest problem. So something like resource availability, or also legal requirements. So basically the demand side was thought to be a bigger challenge. And similarly, they thought the lack of experience in the beginning was a challenge, the way they are qualified in the organization. And of course, it's not surprising that after the pilots, experience was not really perceived as a challenge anymore. So this was definitely something where we can say, okay, piloting does contribute to capability building, to organizational learning. So that is basically confirmed, not very surprising. But what is a little more surprising, I would say, is that, for example, costs were initially not really thought to be a huge issue. And in the end, that was one of the main points that the companies and the leaders were mentioning, alongside with supply chain. So you can see that there is a slight shift from more focus on the demand side, where they were worried that the market basically wasn't ready to take their circular offers. And it shifted to more of a supply side challenge, where It's about, okay, how do you collaborate along the supply chain? For example, if one organization switches to circularity, how do they bring along the other ones? Are they interested in this? How do they have the necessary knowledge for it or resources to invest in new infrastructure? So these are all questions that came up throughout the pilot projects, which just makes it clear that yeah, you're really diving deeper when you're doing those pilots, and you're really understanding where the real pain points are. And then the other thing, cost, was something that increased a lot. So they realized, okay, there is a potential, because the financial factors also rose as a motivation for doing those circular business model pilots and implementing the circular business models. But they also realized that they really have to work on the cost side to be able to make it financially viable. Then next up, we asked about where on this R scale, along the R strategies, they see the greatest potential. And just to refer back really quick, so we have those 3 categories, R0 to R2. That's those here that happen before the production. And then we have all of those here in the middle. That is this whole block. And then on the bottom, what we called downstream waste valorization is the recycling and energy recovery, so the very outermost cycles. And we can see that the biggest potential was actually seen in this top block here. So upstream circularity facilitation, so basically design and rethinking, refusing also, so really reducing the material input. Is what has been seen as potential, which is interesting because this is regular companies that have done this. This is not necessarily companies that from the beginning were incredibly excited about circular economy. And you can see that also in the beginning, if we just briefly go back to the challenges, we see that, for example, experience-related challenges were still perceived as somewhat high. So I think from that we can assume that the knowledge wasn't already there, and that's why we can kind of tell that throughout the pilots, they really understood the benefits of a circular economy, and that the upstream activities have the biggest lever because we were moving in this middle area here, and they understood that a lot of these things can only be done effectively in a circular way if those earlier points have been considered as well. I should also mention that for projects did say they see no further potential, which of course can also happen in a pilot project. What was interesting here is that there was a bit of a difference between the product service system pilots and the remanufacturing pilots. So here you see 3 of those were product service system pilots, and just 1 was remanufacturing that saw no further potential. And so we can already kind of understand that there is a difference in how easy or difficult it is to implement those types of business models. So to wrap it up, I would say there's 2 main findings or takeaways that I would at least take from this study. That on one hand, we have a market that seems to be ready for circular business models. Of course, this is not a generalizable finding. It's an indication that that maybe the worries within the companies are bigger than the actual challenges on the market. And that the pilots were effective in providing experience, addressing question, and really helping those businesses understand what are the true pain points that need to be solved. But we also know that cost is something, and supply chain issues are something that really needs further attention. So I think looking inside and seeing how can we change our organization so this business model becomes viable also financially, I think that's a very important part. So that's what I would say. Any organization looking to change towards circularity, it's really about building this capability and getting this experience before this transition is really done on a larger scale. And then the other thing was that we saw that the product service systems those pilots were struggling more because a product service system is just more complex, as I introduced in the beginning. Whereas, for example, remanufacturing, it just requires, as I showed you in the example, they were able to 3D print some spare parts and basically do their entire process as they would with spare parts that they would just buy or regular assembly of a new product. So it doesn't require as many changes. I think that can explain why some of the product service system business models didn't see so much further potential. And what we also figured out through this data is that if you include calculations, very detailed calculations, too early in such a pilot process, you can really hinder innovation because you're already saying, well, this is going to be too expensive, this is not going to work. And so it's really a danger for this open experimentation, open piloting to really gather information and try out innovative approaches. It's really important to obviously have an idea of the cost in the beginning, but then throughout the process, nail that down further. Because if you do it too late, that is also an issue. If the costs are only considered after the pilot, then there can be the feeling of, okay, this was so expensive and we don't even know how we can reduce the cost. And so we shouldn't even do it in the first place. So it's really about finding that sweet spot of when you want to look at the costs more. And I think it's about building a business model iteratively. It's about testing it and refining the financial model with the first data that you're getting, and especially if a pilot project lasts 2-3 years, I think there's many opportunities in between to continue refining the business model. So in the end of the piloting phase, you actually understand how it can be made financially viable. And I think also for public tenders, which this was a part of, it was publicly funded, I think a takeaway would be that it makes sense to not define a business model in the beginning, to say, well, we want to see some product service system business models, or we want to see some remanufacturing business models, but to say that we want to achieve circularity and we want to achieve it in a sustainable way, and then to see what business models develop throughout. Yeah. So that's it from me. I also included some QR codes if you want to go take a look at the article on the right-hand side, or if you want to connect with me on LinkedIn. I'm happy to continue the conversation. I'm looking forward to any questions. Thank you.
Yeah, thanks a lot, Julian, for highlighting this really important topic. Because when sustainable technologies are available, they ideally need to enter the market. So also suitable business models are key. So for the audience, again, indeed, post your questions in the chat. I'm happy to address them to our speaker. Maybe to start off, I really like the shift from selling products to selling service. I mean, if you think of Netflix, for example, you know, we don't buy DVDs or whatever. It's really the service that is being offered. But if you connect that to, for example, the molecules and materials that were discussed in the previous two talks, which segment of chemical products do you think service-based models are really an eye-opener, really an opportunity also to drive sustainability of those products forward?
I think for chemicals, of course, it's difficult for chemicals themselves to be shared or to be rented, I suppose. I guess if you can use a chemical in a process that then in the end comes out the same way as it went in, I suppose you could reuse that or just rent it to somebody. But I think the bigger potential here is to share lab spaces, laboratories, and to share equipment. And I think this could also be done through rental models or some other cost and revenue sharing agreements where maybe you have some storage for different types of chemicals, maybe some that needs very high or very low temperatures. So of course, these are expensive equipments. And I think similar to other industries, there is a potential, especially for smaller companies, or for startups to work together with bigger companies to share some of this infrastructure. And I think we're seeing some of this already, but I think what I always like to stress here is that we really need to set up good governance structures for such collaborations, because I think cost and revenue sharing is something that in the circular economy space we like to say a lot, because sharing sounds great and we want to collaborate. But of course, from a business perspective, that's always connected to a lot of risk and uncertainty, because you don't really know maybe all these partners, and you don't have full control over your resources or your infrastructure, your capital goods. So there's a bit of apprehension, and I think a way to bridge that is to implement very clear governance structures, responsibilities, to say, okay, who contributes what and who gets access to what. And I think we really need to see some more good examples of how this can be organized in order to implement it on a wider scale. But I would love to see some more research on something like this, for example. And I'm hoping to see parts of this, at least also in circular economy standards.
Yeah, fully agree. And I mean, I know this example of Philips that designs light bulbs. And at one point, someone went to Philips and I think it was a he, but anyway, he said, I don't want to buy any light bulbs. I just want light. Where can I sign a contract? And I don't care what you do with the light bulbs, but I just want, light intensity, this amount, and fix it. And that really drives the focus, not for making many light bulbs, but actually to sustain light bulb production and recycling, and also for solvents used in chemistry. I also learned of a few companies who actually develop surface-based models that after the client uses the solvent, it actually goes back to the producer. And what could be a major advantage is that the producer who makes the product also should have the expertise, or should develop the expertise for the recycling, so the cleaning up of the product and reselling it. So do you think, if you think of policy standards, maybe from a policies perspective, we should stimulate or make it mandatory, or at least the attempt mandatory, to include service-based models, just to make the producer more responsible for closing the loop and also facilitating closing that loop?
That's a good question, because that's basically one of the core things that we're always discussing in standardization. How much should we actually say what companies should do, and how much do we just give very broad targets? And there's good arguments for and against both sides, because of course we don't want to prescribe what kind of business model a company should do, right? That is a generally very new thing. Actually, I'm involved in the standardization for circular business models, and of course we cannot tell companies you should implement this business model for your company, but we can try to give some guidance on, if you want to transition to circularity, these are some things that you should be aware of, or that you should consider at some point in this process. But it is a very new field, and I understand also when people say we need some guidance because there isn't so much knowledge there yet. I would be a little bit cautious in saying we need more service-based business models. I would say maybe we need more business models where we can trace the materials. So we need more transparency, resource traceability. We need more collaboration, which can result or would result in sharing logically. But I think I would encourage those maybe underlying things more, and then say, well, we want to achieve with this is what we want to achieve is sustainability. And I also like to stress this always in the circularity debate, that when something's circular, it's not necessarily more sustainable than a linear option. So we really need to always look at how sustainable is it really, and then see, does a circular business model make sense here in terms of sustainability, or does it not? Most of the times it does, but not always. And so I think we need to understand what is actually the goal here. Is the goal to be circular or service-based, or is the goal to be more sustainable? And I would say it's definitely the latter.
Yeah, fully agree on that. just to stress, circularity is not a goal, but it could be a means to a solution of waste problems that linear models have offered us.
Yes.
Just one more before I focus on Sylvia's question. I really like to put more responsibility on the producer for closing the loop. And I mean, you highlighted supply chain. I mean, a chain is still the linear thinking, let's say. So do you see opportunities to also focus on supply cycles and by default create this circularity thinking in not wasting resources, not wasting products, but let's try it on a product level to close the loop and how producers can facilitate that?
I mean, that is a big question and a big topic, but obviously very, very relevant at the moment. I would say I'm speaking of supply chains because that's what the questionnaires were, that's what the surveys asked for, and that's essentially also the status quo, right? I mean, we are still working with supply chains for the most part, especially when it's international and it's sometimes difficult to understand exactly where something's coming from. In the standardization world, we're actually talking about value networks. That's kind of the term that seems to be emerging in this sense. So it goes into the direction of a value circle, but recognizes more that also within a collaboration along supply circles, if you will, it's not always a closed system. It's not always a closed loop. So value networks, I think, is more what will actually have to be the future if we want to move to a more circular economy. And I think there are parts that are being put into place to make this possible, right? We're starting with legislation that requires certain amounts of recycled materials in products and packaging. We are rolling out the circular the digital product passport for information on circular products. So there we will see how easy it will be to integrate supply chain partners or value network partners into a circular kind of mindset. And I think it will take some time, and I think it will be the task of individual companies at the beginning within a supply network to push for circularity and to encourage their partners to do this. And I think then over time we will see hopefully a digital product passport that creates more transparency along supply chains and networks, and also for the end consumer, of course.
Yeah, no, that's a really good point. I mean, in circularity, we often tend to think of the material world, but it's much better to focus on retaining value, retaining the function of a product, than to just look at how we can move resources continuously. Sylvia, our next speaker, highlighted in the chat on slide 6. This one indeed, could you elaborate a bit on what could be done with neural networks for the spare parts? She mentioned that they develop different disassembly parts, for example, or paths.
Yes. So what they did, as far as I understood, and I have to say I was not involved in this pilot project specifically. I mean, I analyzed the data on the motivations, challenges, and potential. But and I encourage you to also check the project website. All the information is also, or the interesting parts about that are also online. But as I understand it, they wanted to figure out also how to disassemble the e-bikes or the spare parts that they wanted to remanufacture in a way that is the least destructive, because that is often the issue, that you have products that are created not to be repaired or disassembled, but essentially products that are glued together or somehow joined together in a way that it makes it very difficult to disassemble them. And so instead of just hacking it apart, basically, this consortium tried to use neural networks and put in the data about the products, of course, and then to get disassembly paths suggested to them. And then I'm assuming, I haven't seen the data on the disassembly, because for me that was not the focus of my research, but I think it's a very interesting question. But I'm assuming that then they were shown these different paths, and what would make sense to me is that then they can see, okay, if you take apart this thing first, then maybe you're destroying that other component a little bit, so you would have to replace that as well. But then you can access those maybe more hard to come by components or more expensive components without destroying them. And then they can choose, okay, which parts can we 3D print, for example, which parts do we have from the manufacturer, and which parts do we really need to preserve throughout the disassembly process. And so I think a neural network can, of course, do this much quicker and much more efficiently than taking apart a bunch of bikes and understanding, okay, what did we destroy in the process and what should we prevent in the future? So that's as much as I can say about that, I think.
Yeah, perfect. Thanks for elaborating on that, and Julian, thanks again for your very informative talk and discussion.
Thank you.
So the last question was addressed by our next speaker, Professor Silvia Gross. She's full professor of inorganic chemistry at the University of Padova, and also serves as DFG Mercator Fellow at Karlsruhe. And she is also, next to research, heavily involved in teaching. She coordinates the International Master's Program on Sustainable Chemistry and Technologies for a Circular Economy. And she's also very active in organizing schools for PhD students on sustainability and circularity. Happy to work together with you, Silvia, in your role as associate editor. And the focus of the lecture, as highlighted on the slide, is really about exploring chemical space with a focus on the design of inorganic materials for sustainability applications. So, Silvia, the floor is yours.
Thank you very much. And can you hear me? Yeah?
Yeah.
Okay, thank you very much. And first of all, I would like to thank the editorial staff of Sustainability and Circularity Now for having invited me. And by the way, I'm very happy to be part of the crew in the editorial board. So as Chris outlined today, my talk will be a very different topic with respect to the previous one. So I will focus on the exploration of the chemical parameter space in order to optimize suitable and sustainable and rational-based low-temperature synthesis for crystalline inorganic nanomaterial, with special focus on environmental and catalytic application. So this is the outline of my talk. First of all, I would like to elaborate a little more on the motivation beyond our experimental efforts, which are the achievement of crystalline nanomaterial at a very low temperature. And this will be the basis for introducing you the synthetic toolbox we have been developing in Padova in the last 10 years, I would say, for preparing different kind of inorganic nanomaterial by low temperature synthetic routes, typically wet chemistry and colloidal one. And one of these routes, which we have used a lot so far, is the low temperature subcritical hydrothermal synthesis, which has been applied to the preparation of well-controlled spinel oxide. And recently this route was implemented specifically for a subclass of this spinel oxide, which are high entropy oxide for application in hydrogen production. So motivation, we are within the very broad framework of sustainable development, which I do not need to introduce. We occupy a niche, which is the one on the environmental pillar, of course, which is related to sustainable synthesis and the preparative approach. And in this sub-framework, we have worked a lot and optimized very different routes, which have been also summarized in some review paper published recently, and last year we published with the Royal Society also this book on unconventional green synthesis of inorganic nanomaterial. So why crystalline inorganic nanomaterial? It is quite straightforward that an ordered structure in the material is strongly related to functional properties, which are listed here. And specifically, for instance, I would like to mention the catalytic ones, which are strongly affected by the exposed facet in the inorganic nanomaterial. It is not only crystallinity which attracts our interest, but also the control of the shape, the so-called anisotropy of the resulting material, because it is quite clear that anisotropic structure are related also to changes in the band gap of the material, and in turn these again affect optical properties, magnetic properties, but also again relevant heterogeneous catalytic properties of the final materials. And in this field, inorganic synthesis represent a very exciting playground, since by changing some of the different experimental parameters involved, we are able to tune and to control the form and the shape of the resulting inorganic crystalline system. This is in this very nice example taken from the literature. You can see as by changing simply the length of the diol used as a structure directing agent for different platinum multiples, they were able to strongly control the shape. Again, back to the general framework is, of course, the one pioneered by John Warner and Paul Anastas, the one of green chemistry. And within the 12 principles of green chemistry, we are focusing on the sixth one, which is energy efficiency. It is known that chemistry production is an extremely intensive, energy-intensive industrial sector. Thought it should be outlined that in the last 35 years, the energy in chemical industry was able to reduce by about 50% its energy consumption. And these efforts goes further. Thought chemical production means to use energy and raw material to achieve new material, new products, and this is very important. Therefore, a strong commitment should be put on optimizing the process, because we cannot avoid thermodynamics and kinetics are ruling, and therefore chemical reactivity is obviously underpinned by the law of thermodynamics and kinetics. We need a given input of energy to overcome the activation energy of the transition state, and this energy input can become a substantial component in the overall environmental footprint of the material. Therefore, we have different tools as a chemist. We can either resort to catalyst, which is the straightforward tool to reduce the activation energy, or what we are trying to do is also implementing new synthesis route in order to comply with the principle, the sixth principle, which states that energy requirements should be minimized, and if possible, synthetic methods should be carried out at room temperature, which is the reason for the low temperature of synthesis as a target. So crystalline material, low temperature of synthesis, but not only. We are trying also to comply with other further synthetic requirements, which are also the shortening of the processing time, again in view of a reduction of the energy consumption. And then our synthesis should be carried out with environmentally friendly solvent, not only water, but also polyols, dipyotetic solvents, supercritical solvents, with earth-abundant precursor to address the relevant topic of criticality of critical raw material. And last but not least, the synthesis should be easy to implement, reproducible with high yield, high throughput, and possible also in view of industrial application scalability. And as mentioned, we also aim to control the shape, the size, and also the doping, the composition. This has led us to develop a quite broad and wide synthetic toolbox with my group in Padova, which I warmly thank. And this toolbox is composed of different routes, which are highlighted here, also used in combination. So for instance, hydrothermal and mini emulsion, hydrothermal and continuous flow, which are characterized by typically low or even room temperature of operation. And by using these routes, we have optimized very different inorganic nanomaterials, which are listed here. And you can see that they could be achieved at either room temperature or low temperature, and they are oxide, sulfide, halogenides, and metal nanoparticles. And specifically for the environmental and catalytic application, you can see that we have optimized a plethora of different inorganic systems for gas exhaust abatement, oxidation catalysis, photocatalysis, and as mentioned in the case study, hydrogen evolution catalysis. So when optimizing our synthesis, we have a lot of different experimental parameters to be taken into account: pH, nature of the solvent in terms of viscosity, the dielectric constant, density, chemical nature and molar ratio of the precursor, nature and amount of additives, ionic strength, and then depending on the process we are using, time and temperature of thermal processing, flow condition, mixing condition, pressure, and so on. So a big amount of different parameters which have to be carefully optimized. But a typical one variable at a time approach, the so-called OVAT approach, process is very demanding in terms of time and consumption. Therefore, whenever we want to reduce the consumption of energy, reagents, solvent, water, we have to reduce the time. Okay, we have PhD students who can work in the lab, but we have to rationalize their time. And also, in order to avoid reaching a suboptimal setting, we can resort to design of experiment, which is a statistical approach in which you can more or less optimize in a given and limited number of the experimental parameters. And this avoids also you to avoid to miss interesting part of the experimental landscape. Since you can change different factors simultaneously and then identify those factors, those parameters which are more relevant in affecting the output of the synthesis. So you have controllable input factors which are chosen by the operator. You have a given process, let's say the kind of synthesis, and then you have something you can quantify as an output measure. And then as chemists, you know that you can also have uncontrollable input factor, which however you are able to identify. So as an example, we want to prepare alloys, a nanoparticle of platinum and palladium, starting from this precursor by using the hydrothermal condition, and therefore our controllable input factor are the pH of the starting solution, the time of the hydrothermal heating, and the temperature. The process is the hydrothermal synthesis, and the output measure, for instance, we can take the Ferré diameter of the final nanoparticle. As uncontrollable input factor, we have this precursor, which in solution can undergo also oligomerization equilibria, which however depend on the concentration, on the temperature, also on the on the nature of the precursor. So they are not so easy to be controlled, but we are aware of them. Then in a design of experiment approach, so we have 3 different parameters. Each of one is changed upon 2 different levels, so 8 and 10, 12 and 24. Therefore, at the end, we have to perform 2 to the 3rd, so 8 different experiments in which we change independently and simultaneously the 3 different target parameters. And at the end of the day, after the synthesis, after having performed this limited set of experiments, we get a Ferré diameter, which we measure by TEM. And what design of experiment, the statistical elaboration of this data then provides you as an output is, for instance, that in this case, the most important parameter in affecting the given synthesis was the pH. So this is what we can do with the design of experiment, what we use in our synthetic optimization to support the experimental work. Okay, so let's see some example. We have been working a lot on hydrothermal synthesis, which is a heterogeneous reaction occurring at a temperature which is higher than the boiling point of the solvent in a closed vessel. Therefore, we have also the formation of an autogenous pressure, so high pressure and temperature, well below the critical point typically, but nevertheless enough to change those experimental parameters such as solvent properties such as dielectric constant, viscosity, density of the solvent, which are very relevant in affecting nucleation and growth phenomena. The approach is really interesting because you are able to explore unusual crystallization pathway and get the crystalline material which would not be possible to achieve in a crystalline form at ambient temperature and pressure, with the typically short processing time using water as a solvent. The syntheses are very easy, reproducible, easy to implement, and also possibly to upscale, and you get crystallization at a very low temperature, typically in high yield and with a good control over stoichiometry. And we have been using this, for instance, for producing transition metals ferrites, which have this general formula in which typically M is divalent cations, cobalt, manganese, zinc, nickel, and so on. And these materials are not only interesting for magnetic properties, but also because they have been explored also for different catalytic reaction. For instance, we have optimized this synthesis for metal, ferrites, for ternary oxide, in which we start from a solution of the two targeted cations with oxalic acid. Then we add TENOC as a peptizing agent. We basify it. Therefore, oxalic acid is deprotonated. You get the co-precipitation of the oxalate, which are highly insoluble. This is not only anymore a solution, it's a suspension, which is hydrothermally treated to get eventually a powder, which is then purified by the workup is based on typically washing and centrifugation. And at the end of the day, you get extremely pure and crystalline oxide of the targeted metals. We have implemented ternary ferrites, but also quaternary with a different composition for the targeted application. We have mentioned that among the different synthetic requirements we want to comply with, it is not only the reduction of the temperature, but also the reduction of the processing time, because this also leads to a reduction of the energy consumption. And interestingly, we have performed this ferrite synthesis by taking out the reactor, the hydrothermal reactor, not only after 24 hours, but also after 1, 3, 6, 9, 12 hours. And what came out was a very interesting result, that the crystallization of the targeted ferrites occurs in all the cases between 1 and 3 hours, which means that we do not need to heat 24 hours. We just need to heat 1-3 hours with a much lower environmental footprint of the synthesis. And also what is very interesting, everything which happened within the autoclave happened within this first 1-3 hour. Afterwards, we do not observe any further growth of the particles. So it's really enough to heat 3 hours. Okay, this approach has been recently implemented by my engaged PhD student, Davide Vendrame, who has developed a low temperature synthesis of high entropy oxide for possible application in oxygen evolution reaction. High entropy oxide are multi-cations oxide. In this case, again, we targeted the spinel structure, which are very interesting as electrocatalyst. And in these cases, a further and additional stabilization is provided by the configurational entropy term, which derives from the co-presence of 3, 4, 5, 6, also even 7 different cations within the spinel structure. And okay, this stabilization is typically favored, of course, as you can see here from the clear expression of the delta G by high temperature, but we were able to get extremely pure and nice and homogeneous oxide also at low temperature. So Davide prepared these high entropy oxide are typically prepared by highly time-consuming and high temperature solid state approaches, which means very high energy consumption because we need to heat for a longer time at 900, 1000, 100, 200, 12,000 degrees C, but Davide was able to optimize a quite low temperature of different oxide by implementing the already described hydrothermal route. So the approach was very similar to the one I described you, and we targeted the different composition which are seen here, and very interesting, and again as a proof that hydrothermal synthesis enable us also to control the final stoichiometry. ECP-OS data confirmed that Davide was able to achieve in the final oxide the targeted stoichiometry, quite carefully controlled, so as you can see here. In all the case, we could get also crystalline material, thought with some differences between the different phases, and in some case, we had some spurious phase which could be eliminated by a further thought very short calcination step. So 500 is quite high, but for only 1 hour to get the final pure phase. And what is also interesting is that by increasing the number of metal from 2 to 3 to 4 to 5 to 6 to 7, we get an increase of the crystallinity, which could hint again to a possible effect of the stabilization of the structure by these configurational entropy terms, which is also highlighted in this figure taken from the literature. High resolution TEM and selected area electron diffraction analysis on 2 different high entropy oxide composed of 5 and 6 different cations evidences the presence of very small particle with a homogeneous spinel structure, and the side data were compliant and in agreement with the XRD pattern, that confirming that the phase purity was at both the micro and the nano scale. And the ADX mapping show also a quite homogeneous distribution of the elements within the multinary oxide, thought some agglomeration of chrome was pointed out at grain boundaries. Thought we did not observe any phase separation or elemental segregation. As I told you before, these are very preliminary data, not yet really metabolized, but within a stay at the KIT in the group of Ben Breitung and Simon Schweidler, Davide also performed some preliminary electrochemical characterization for the application in the oxygen evolution reaction. And what is very interesting, we could see that by comparing the high entropy oxide with the benchmark iridium oxide, the material were performing quite good, and specifically these here highlighted here were even more active than iron oxide at the 10 intensity milliampere per centimeter target current, and these data are of course normalized over the effective electrochemical active surface area. So we are also encouraged by this quite preliminary but encouraging and promising data. So I wrap up. In conclusion, I hope to have convinced you that by developing a broad and interconnected synthetic toolbox, it is possible to explore very different material with very different composition and stoichiometry with short time, low temperature, and in a reproducible and upscalable way. It is very important to support these experimental efforts by tools such as design of experiment. We are also working with people performing life cycle assessment to quantify the real environmental footprint of our synthesis. And I could not show you the example on Syria, but we are also able to nicely control the final anisotropy of the material. And we are now implementing the hydrothermal approach with a brand new equipment we purchased within continuous flow condition and also coupling with the microwave. And what is very important, I had no time to explain it, we are supporting the synthetic approach, the synthetic efforts with careful time and temperature resolved measurement at synchrotron radiation source to follow in more detail the crystallization phenomenon. And with this, I would like to thank you for your attention, and of course my group in Padova, specifically Davide, for the work I have shown you today, but also the different cooperation we have specifically in Germany and in Italy. And I would like to thank you for your attention. Thank you.
Yeah, thanks so much, Sylvia, for highlighting your wonderful results on making inorganic nanomaterials. Again, the talk is open for discussion, so feel free to add your questions to the chat, and I'll start with my first question. You highlighted design of experiments. And I think it is a wonderful tool to guide let's say, the optimization of the experimental conditions. What is your feeling of adding machine learning on that?
Okay. This is a very good question. So first of all, I am not a statistician. I'm not a statistician. Nowadays, we are working with design of experiment quite often in our group, but we are always supported by the expertise of Luigi Salmaso, who is a statistician. And recently, Luigi was also exploring the possibility, of course, to upgrade, let's see if I can use this term, design of experiment by using exactly machine learning. This is the next step we would like to do, also in view, Chris, of machine learning driven material discovery. The idea could be, for instance, in the case of high entropy oxide, not to produce a big batch of different samples, but try also by machine learning, and in this case also other kind of modeling, because the calculation of the configurational entropy could require also other theoretical tools. But the idea would be to foresee in advance which could be the properties of the final material, starting, for instance, from the structure and the stoichiometry. And in this case, the interaction and the synergy between design of experiment and machine learning is surely suitable to strongly accelerate the material discovery. So thank you for the question.
Yeah, I fully agree. And I mean, I think a year ago there was a paper on AI for material design, where actually the experimental validation of the computational design was done a little bit poorly. But I think that in particular is of great interest, really, to do the experimental validation and the computational design hand in hand, ideally, but still lots of work has to be done to bring those worlds really close together. I don't see any other questions yet in the chat, but so let me ask my final one. You focus on wet chemistry, colloidal chemistry, and then you mentioned also flow chemistry already as a new opportunity. So what about solid state mechanochemistry?
Okay,
Is
so yes, I
this
teach.
something that you think
Yeah.
everyone should adopt or should happily ignore? I'm just curious.
No,
what
no,
you
I'm not
think.
ignore. I have a ball milling in my lab. So I bought also for the teaching lab for the chemistry master student. So I really like also ball milling because among the solid state approaches is the only one or one of the few ones which is performed at room temperature, and it provides again the possibility to change through the volume to powder ratio, the frequency of the ball milling, and so on. Also some optimization in the experimental. I know the work of Lars Borchardt in Germany, who has been working a lot on free solvent-free green chemistry by ball milling, and this is, of course, one of the most interesting solid state approaches in view of sustainability. So for sure, we are not using too much, but it's something we take into account. Thank you very much.
Yeah, thanks for mentioning that. I mean, I remember, like, I don't know, 8 years ago, we did a good old mortar and pestle solid state chemistry experiment where the protocol basically was 5 minutes of grinding and 1 day of muscle ache. But,
Yeah, okay,
the
but now,
versions with ball milling machines, yeah, I also quite fancy them. And I look forward to all the opportunities also in sustainability and in circular products to see what can be developed there. So,
okay, yes.
That's Sylvia. Thanks once more, all speakers.
Yeah, thank you again.
Exciting, Webinar. Thanks a lot for your contributions as well as discussions. And then I'll hand over back to Charlie.
Thank you so much, Chris, and thank you everybody for your fantastic talks today. It's been really wonderful to have such a lovely mix of different ideas around sustainability and circularity. So yeah, thank you so much for your involvement. And a huge thank you to Chris, who I think we can all agree has done a fantastic job of chairing this session today. I believe the link to the recording will be available within 24 hours. So if you'd like to rewatch this, you can watch as many times as you'd like. Failing that, we'd love to hear from you on our social media channels. If you just search for Sustainability and Circularity Now, you'll find us on LinkedIn, Blue Sky and X. So we'd love to interact with you further after this. And as Chris pointed out at the beginning, if you're interested in becoming a select crowd reviewer, or if you'd like to contribute to one of our focus issues, information is available on the website, and feel free to reach out to the editorial team or one of our associate editors for further information. But with that, I think I will bring this session to a close. So thank you very much, everyone, for joining, and hopefully see you soon. Take care. Bye-bye.